from an exam day before yesterday. So I'm going to give you a couple minutes to read this. Okay, so you have this county fair, and here is Miss D, and these are your stalls. Okay. So once again, this is the county fair. D is visiting the fair. And these are your stalls, the n stalls that she would have to pass through. And each one of these is giving away a cup, and a cup size is C1, C2, up to Cn. And she cannot come back. She can only go in one direction. And she has to decide how to pick up cups in such a way that they all stack, and in the order in which she picks them up. She can't reorder her cups or do anything with it. So in the end, it looks like that picture up there that says how the cups have to be stacked. The largest one first, the next largest, and then the next largest, and so on. And so the question is, which ones of these cups should D pick up, and which ones should she reject, right? So just to make sure I get the point right, the goal is to get D to pick up as many cups as possible. All right, so n stalls, each stall has a cup. You want to put this back, or it's fine?
Yeah.
Okay. Each stall has a cup of a certain size, and hey, hi. And cup I must stack in a previous larger cup. And if it doesn't, then D has to reject the cup. Well, even if it stacks, it's possible that she rejects the cup because of something that she knows about stalls later on. And you want to maximize the number of cups. So this is the problem from the exam. All right, so the first question, there were a series of questions there. The first question is, why does greedy algorithm not work? Yeah?
Is it because the subproblems are dependent upon each other? And I think only greedy works when they're independent?
That's not quite true. A greedy algorithm can work when subproblems depend on each other. The reason greedy algorithm fails here is, you want to try why greedy algorithm would fail?
Let me think about it. I didn't even bother proving it since you already said it was a dynamic programming question. But
Right, that's true.
let's see. I mean, it will fail because at each point, there's no way to tell if that is your best choice, because you would need to know everything that comes after.
Correct.
To determine
Yeah.
your choice.
So that's where the problem is. Greedy algorithms don't take the future into account. They just have to make decisions based on what they know. So it does not have look ahead. And you can construct these simple examples. So let's say that the greedy algorithm picked A, B, and 3 cups of size A, B, and C. Or let's say the first 3, the greedy algorithm said, go ahead and pick them up. And let's say they are in the right order, which means C1 is bigger than C2 is bigger than C3. Now, can we mess up the greedy algorithm now? How do we force greedy algorithm to do poorly? So for that, this decision is going to be made independent of what comes after. So what I'm going to do is to generate 2 different sequences, where in one it'll give you the right answer and in the other it won't. Okay? So let's say that say it works correctly on a sequence where somewhere here it picks up D picks up a 4th cup of size D. Now what I can do is, since I know the 4th cup is going to be of size D, I'm going to insert a couple of cups here after she picks up C that are bigger than C. Okay? But I'm going to put in 2 cups. So I'm going to put E and F. So let me just redraw this. So here we have A, we have B, we have C, and somewhere here is D, and blah, blah, blah. So what I'm going to do is I'm going to insert here E and F that are actually larger than C, so they won't stack with C, so the greedy algorithm cannot possibly pick them up. The greedy algorithm is still going to go look for that D that comes a little bit later on, whereas if I had skipped C and picked E and F, I would have done better. So it's easy to create these data sets or these sequences. And based on this, here's an example. Right? We can do, so this is A, B, and C, right? And this is D. So here, let's say the greedy algorithm picked these 3. Now I'm going to insert 5 and 4 that are bigger than 3. So if I had skipped 3, I would have gotten to 5 and 4, and I would have gotten more cups. Right? So greedy algorithm can't tell the difference. Right? So that's the general idea there. Sound okay to you? All right, so the next thing that the question asks is, how can I write a recursive algorithm that solves this problem? Okay. So yeah.
So each solve, I guess, we have only 2 decisions, taking it or not taking it.
Right,
So
exactly.
We can recursively call that. And if we do
Exactly.
take it, we keep track of the size we took it at, and we also want to keep track of the count.
Yeah, so that's where the tricky part is. Do you want to keep track of the size or not? And also, you said either pick a cup or not. Yeah. Are you going to talk about the first cup or the last cup? Because I always have one way to think about it, and I know students end up thinking the other way.
So we'd say the first one?
You would say the first one. You?
I know you prefer the last one.
I prefer the last one, that's right. Yeah.
But
that's
I like choosing the first one.
You like choosing the first one. OK, let's go with the first one.
Wait, can we go with the last one? I want to see your approach.
Yeah, so the reason the last one is cleaner is because the subproblems become cleaner. Okay, so you could decide to either pick. So let's say I go with your approach, where you either pick or not pick C1. Yeah. Then you have to write a subproblem that goes from 2 to n, and that's awkward for me to write. Okay, whereas if I say let's take n and either D picks this cup or not. So depending on what happens, you're looking at a smaller subproblem, but they all start at 1. So now I can say it's 1 through whatever. It's conceptually simpler to define these subproblems. So that's where it comes from. I don't have any specific bias. I can handle both. But for you, it is better to structure your thinking because it's because you are starting with one that you are also talking about what you picked up. And that is wrong. Okay? That's where you're going to get stuck because now you have two parameters. One is where you are in the algorithm, and the other is what have I done so far? And that's going to make your life much more difficult, I think. Okay? Instead, if I just say, I want to solve this subproblem, I have no history. Okay? I can start from a clean slate, then it becomes a lot easier. I just have to adjust my decisions later on. All right? So yeah, I would definitely recommend going with recursive solutions. It's always a good idea to say, I want to solve the whole problem. In order to solve that whole problem, what subproblems do I have to solve in order to take care of that? Okay? I don't know if that even remotely convinced you.
No, I see what you're saying because
Yeah.
you start from the first index.
Yeah. So somewhere in your at a general step, you're going to be somewhere here, and you have to worry about what decisions you made previously, and that's going to mess you up because your recursion is not clean anymore. I have to know what the heck I did before, and I don't want to. I want to write a clean recursive solution that says, here's a subproblem that this recursive call must solve, and I don't have that because now I have to bring in the history, which means I have to add another parameter, which means things get messed up.
Yeah, that's how I solved it with adding.
I know, that's fine. A lot of people did that, so I'm not faulting you for it. I'm just, in class, again, there were other problems where I tried to force you to think from the other end. I guess I was not that successful. So let's go with my approach, if you don't mind. We're going to assume that there are two possibilities. Either you take this last guy or not. If you don't take it, then the problem is simply 1 on n minus 1, right? That's easy. If you do take it, then what?
Maybe n minus 1 plus 1. Yes, adding.
Well, it won't be n minus 1 plus 1 because it's possible that this guy is smaller than this. You don't know what your last cup is going to be when you solve the n minus 1.
The recursive solution to.
I know. I'm still talking about the recursive solution as well. So
you check if n minus 1 is
bigger than n.
That's the case. Then 1 plus.
Yeah. If not,
Then you can't include it.
then what is my recursive call?
Return the max of the two cases.
Sorry?
Return the max of the two cases.
Yeah, but your second case got messed up because you couldn't quite, there is no recursive call if this guy is smaller than this.
So would it be n minus 2?
Yeah, but n minus 2 also could be smaller.
I mean, I guess then we probably have to start from 0 to n minus 1.
Right. So this is where defining the recursive problem is very, very important. And that also tells you what subproblems you're going to solve. So they're all kind of connected. Okay. So here is a recursive approach. I'm going to call this help D. Right. So you want to help this person pick up the maximum number of cups in the county fair. I'm going to call help D of I to be the ith subproblem, which is everything from here to here. Okay, so there things become nicer because this is my ith subproblem, and therefore my whole problem is just everything up till here. Okay? So now I have only one parameter instead of trying to remember what I did before, right? And then, so I'm going to define this as return the maximum number of stackable cups in 1 through I. Okay? So it always helps you to think about these subproblems, because that's how the rest of the dynamic programming gets solved. So there's some initialization. So you guys are almost there. Essentially, if n-1 doesn't work, you have to go to n-2, but then you don't know how far you have to go. So as you said, you just start from the beginning. And what we are going to do is you're going to go from k equals 1 to I-1, because you're solving the ith subproblem. If the kth cup is bigger than the ith cup, then number of cups is going to be maximum of number of cups, or the solution for k plus 1. Essentially, you're trying to find the best among all the possible k's, right? So that's the same as saying, let's initialize to 1 and then see if we can do any better. We could have gone the other way from I-1 down to 1. That also would have worked. But either way, this is one way to solve the problem. In the end, what are you going to return? Well, you're just going to return the whatever it is that you computed here. Okay, this is almost a trivial solution. It just says solve all those subproblems. So in order to solve this, I'm going to solve every subproblem here where the last cup is bigger than this. Otherwise, I'm not interested. And from among those solutions, one of them must be the largest, and that's what I'm going to use. So here, I didn't use any of my what did I do before kind of thing. I didn't keep track of the best, of the smallest one that I had, and so on. Yeah? Yeah?
So with this algorithm,
yeah,
you always will be taking the first cup?
Correct. Well, no, I'm not always going to take the first cup. I am, so let's say the first cup, if I'm solving the problem for I equals 1, there's only one cup, so I'm going to just take it. If I solve it for I equals 2, it's either going to be the number 1, because that's how you initialize it, or it's going to be one more than what you got for this, as long as this is bigger than this.
Oh, I see.
Otherwise, I don't care.
Yeah, okay. Yeah, it's
right? But that's exactly what this condition is.
Yeah.
So what you guys talked about in terms of keeping track of the largest cup you picked so far is built into it now. Okay? Because I only consider those subproblems where that last cup is k and that k is larger than this. So another way to think about this subproblem or this recursive call is help d of I. In fact, I didn't quite write this correctly. It's not just the maximum number of stackable cups, but it's also, it must include the ith cup, right? So let me add that there and make sure that we say this right. That includes cup from stall I. Is that good? Okay.
in the grid.
Sorry?
So,
Yeah, I have to do that again. Okay. So this is a recursive solution. Now, if I want to solve this if I want to solve the whole problem, what do I do? This is only this only is that recursive part. Doesn't quite solve the problem. Help D of n will only give you solutions where the nth cup is included. Because that's how we wrote the problem.
so you have to check for every n or n minus 1 or n minus 2.
So you just go and look at the best of the solutions of all I and pick the best one. So help D of n may not be your best answer. So you solve all these subproblems and pick the best. Okay? All right. So the subproblems, if you look at it, you're making this recursive call here, right? And it's done for different values of k. You don't know when you're going to need what. So essentially, if you look at all the subproblems, these are all your subproblems that you're going to solve. You're going to start with help D of, well, it doesn't matter where you start. These are the recursive calls that are ever going to be called by any of those instances, right? So this also answers another question in the exam that said, what are all the subproblems you're ever going to need? Now, if you were to include that other parameter of what was that last cup you picked, then you have a lot more subproblems to deal with. For each I, you have to look at every possible j that's your last cup. Does that make sense? Now I don't need that. Okay? And remember, the cup size is a real number. So I can't even try all possible cup sizes, right? Other than the ones that are already used. And also the memoization that I need is a simple array where D of I is the optimal solution for stalls, for the first I stalls that includes the cup from stall I. Okay? So you need to remember that the final solution is not D of n, but it's the largest in the entire array. That's the only thing you have to remember here. Okay? So recurrence relation, the key thing. How do I write this now? What is D of I going to be? Is that easy?
Yeah, let me see. It will be D of I equal to the max of the current D of I, comma, D of k, and k runs from 0 to
Right.
I minus 1.
And one more condition there.
The cup, like j, has to be bigger than I.
Right. That's right. So you roughly got it right. There were a couple of little glitches there, but this is the answer. D of I is the largest of dk plus 1, where the cup of size k is bigger than cup of size I, and k is somewhere between 1 and I. Okay. Now you also need to know where the recursion starts. So if you don't find any that satisfy that condition, if everything to the left of I is smaller than the cup of I, then this is just going to be 1. We just have to take care of that little case, right? Is that clear? I can actually rewrite this in a better form by adding an extra stall at the end. Call it stall 0, where I have a cup of infinite size. So she's always going to pick this. But now I don't need to add this other extra condition because I can write this more simply, where this goes from 0 through I minus 1. And I know that d of 0, I'm going to set it as 0. Right? I actually should have set it to 1, but then I don't want to count that fake cup that I picked up at stall 0, so I'll set it to 0. Okay?
But if you set it to 1, then if you use it, you're going to have a count of 2. So
Yeah, so I have to reduce 1 at the end then. So I might as well set it to 0. But the good thing now is that I don't need that second condition here that says, what if all those values are bigger? It's never going to happen because I have a safeguard there where there's an element there that's going to be larger than anything you have there. Okay?
Yeah, it didn't include like some of the deal. Like when I was making the recursive solution itself,
Yeah.
I didn't initialize every d of I to 1 before using that. But when I was writing the recurrence relation, I didn't put that there.
That's fine. Look, there may be many ways to solve this problem. This is just my version. I just think it helps to streamline your thinking because then you can apply it to many problems in a uniform way. But yeah, in general, there are many ways to solve this problem. You could have perfectly well have solved it the other way, where you were thinking of starting from the left hand. That also works. It just makes for lots of awkward things that I don't like. So this, in my opinion, is the cleanest version. So if you want to know in what order to solve these subproblems, it becomes clear because you want it in such a way that whatever you need is solved prior to when it's needed. So obviously you want to go from D1, D2 up to D of n, right? So that means your non-recursive algorithm is going to be quite simple. Oops, sorry. You can see this. You start with d of 0 equals 0. You start with a cup at stall 0 to be infinity. That's just stuff that you add. And then you go for I equals 1 to n. This is the recurrence we had on the previous slide. And at the end, you have to remember not just to return d of n, but to return the largest of the values. That's your non-recursive code. Right? Cool? Questions? So it should be obvious that this is n squared. Right? Now, so you need to also notice that this problem is something you guys we have solved here in this meetings. It should remind you of something else. Does it?
The LIS problem.
That's right.
The what?
The longest increasing subsequence problem, except that it's not increasing, it's decreasing. Remember, your cups should be of decreasing size. So you're finding a subsequence that's the longest, and that's decreasing. No different from increasing. You just have to flip the signs, the sign of the relation, and so it's. And when we solved the LIS problem, you saw that it's really the LCS problem in disguise, because if you take your sequence and you do the longest common subsequence with the sorted list, you essentially get LIS. So over here, there's a simple solution where you say just do an LCS of this sequence of numbers with the sorted order of that same sequence. Let me write that clearly. So LIS, that's the longest increasing subsequence of some sequence of number C, is the same as the longest common subsequence between C and sorted C. Okay. Now it doesn't matter that C is a set of real numbers. We're just thinking of them as characters now. And we're simply taking the sequence of numbers that we have at the stalls. Then we sort them and put them in the sorted order. And now if you just find the longest common subsequence, it's going to be the same thing. Of course, if you want longest decreasing subsequence, what do? You do C with reverse sorted, right? So if you reverse sort it from largest to smallest and just run the longest common subsequence, it'll give you the longest decreasing subsequence. So you could have solved this in one sentence and then said, oh yeah, longest common subsequence. Look it up in the book. Okay? And we know this runs in order n squared. And the sorting runs in n log n, so it's still n squared. So you need to just see these connections between the problems you previously solved. Only then will you start to feel comfortable with these problems. Okay? Are we good here? Okay, so next I'm going to spend a few minutes on how to make this faster, how to make this more efficient. N squared sounds a little unfair. Can we do better? Right? Where do you think is the weakness in the algorithm that you could make it faster? Clearly, if you go the route of longest common subsequence, you're sunk because longest common subsequence runs in n squared time. We don't know how to do that better. So we need something completely different.
Completely different from that.
Yeah. Forget all this. I should erase this from the board. Otherwise, you're going to be locked into that, and that's all you'll be able to think. The issue is obviously the for loop. Very good. Yeah. So let's go back there, right? Yeah, here it is. In order to find this largest, I have to find all the k's that are larger size than this. If I can do that quickly, then I'm fine. But in the worst case, everything to the left is larger than this guy, which means I'm going to end up spending a lot of time. Do I really have to go and look at all of them or not? That's the question. So this is a little bit harder. And I don't expect, by the way, I was not expecting the more efficient solution from any of the class, from any of the students, but this is for the advanced programming team, yeah? And it's non-trivial, so it's a good idea for us to think about this. Now, let's look at C of I. Let's look at the ith subproblem. I am here. I want to know what is D of I. What's the best solution for this subproblem with I elements, right? So in order to do that, I have to figure out all the, we said that we have to figure out all the values of these cup sizes that are larger than this guy. Yeah?
Great. This is just an idea. Can we have an augmented, augmented binary tree where, let's say we look at.
What am I doing? The binary tree has to have, must come from something.
Mm-hmm.
Is it What is it organized based on?
The size of the cup.
So you mean you're putting it in sorted order?
Yes, but each node has the size of that cup and where in the array.
Ah, I see. Okay, so you're going to, okay, but so you're saying it's a binary search tree that where the key is the size of the cup,
Yeah.
but then you're also storing the information on the index.
Yeah.
Okay, good. Yeah, so then you want to find, so let's say you're looking at CI, it'll find it somewhere, and now you're going to look at the entire subtree, the stuff to the left of it, and then you're
So
going to do what?
We want CLI to be smaller, right? So we will look at the right subtree and count the number of nodes.
So let me stop you for a second and ask you, what is your goal? Your goal is to find all the guys that are larger than I,
Yeah.
then or only some of them.
Yeah. All
If you're going to find all of them, then you have a problem because in the worst case, everything could be larger. What are you going to do? That's too many. Right?
I don't know if this even makes sense, but like when going back, maybe C, like let's say we're at CF, right? When we're at CF4, maybe we can compare the index of CF4
Yeah.
and the value of CF4 to see if there's anything to consider before from 1 to CF4.
So let me drag you in a different direction. Okay. Your ideas are there, but it's missing something important. So if I may, I'm going to take you away to a different approach. Now, let's say that I'm keeping track of all the solutions. I'm looking at the ith subproblem, and I'm keeping track of the best. I can work here. Sorry. So how does this work? Yeah. Let's say that I find at least one solution where, so by the way, just remember that I'm in iteration I, just for reference. Let's say that I've found a best solution of length 1. Meaning D has only picked one cup. I picked another solution where she has picked 2 cups. I picked another solution where she has 3 cups, and so on and so forth. And I have something that goes up to some number here. I don't know what that number is. Let's say 7. Now, there may be more than one solution where you picked 1 cup, because remember, you've solved a whole bunch of subproblems, right? Some of those subproblems will fit here. Some of those will fit here. Others will fit here, and so on. Now, if there is more than one of any of these categories, which one do I have to keep? Do I have to keep all of them?
Wait, can you repeat that again? Sorry.
Yeah. So let's say that I have 2 solutions with say this bottom guy, this 7. So here, let's say I picked up 7 cups. Okay. Let's say that there are 2 of these, meaning I could have picked 1, 3, 5, 7, 9, or I could have picked 1, 2, 4, 6, 9. Same, they would have both given me 7. Of these 2 possibilities, which one should I keep track of both, or do I have to only worry about one of them? In order to solve the ith subproblem. whatever is the last cup.
If 7 is the last cup, then you only need to keep track of 1 because you
True, but that's true. But then, if I have more than one solution, each one would end up at a different point. Do I have to keep track of all of them?
Yeah, if they end up at different points, you keep track of all of them.
Should I keep track of all of them?
And you want to keep track of where the 7th cup is the smallest?
Smallest?
Oh, no. Wait. No, biggest, yeah, because we're
Biggest. Yeah, biggest.
Yeah, it is.
So
sorry.
all I have to keep track of in each of these is one solution where the last cup is the biggest possible. Okay? The others I couldn't care less. Why do I care? Right? If I can fit this cup into that one that ends with the biggest cup, I'm in good shape. Right? So what I'm going to do is keep track of one solution of different lengths, where in each one it ends with the largest possible cup that I can. Will this help me? This sounds crazy. What do I do with this? So remember, I'm in my ith iteration. I'm looking at the ith cup. I've solved a whole bunch of subproblems, and each one, I've kept track of some of them. I've thrown away some others. Yeah.
Okay, if that's the case, then you don't need to try everything. You only need to try the different endpoints of the lengths that you keep track of, and then like.
But what if I have one of each length, and there are lots of them?
What if you have one of each length, and they are like, oh, okay, then
Yeah. So at this point, you're supposed to notice one more interesting thing. Remember, I only kept one solution of length 1, one of length 2, and so on, right? Now, each one has a last cup size. So let me say that this value is f of 1, which means among all the solutions with 1, this is the solution that ended with the largest cup. And that cup size is f1. Let's say here it's f2. Among all the solutions that have length 2, this is the one that's the best in terms of the largest cup size for the last guy, and that cup size is f2. Here it's f3. Here it's f7. Now, can you say anything about f1, f2, f3, f4, f7? Can f2 be larger than f1? It's not possible, right? Because if it were, then I should be able to do better with that one. So it just doesn't make sense, which means great, which means these values are now decreasing perfectly, monotonically. Because I can apply the same argument and say f3 cannot be smaller than, f3 cannot be larger than f2. Right? So this is looking better. Now what do I have to do? So I'm here in the ith subproblem. I've looked at all the subproblems here. I've looked at all their solutions, and I've condensed it into this structure where I have a solution of length 1, a solution of length 2, a solution of length 3, and so on. And I've kept track of the best last cup for each one of those, and they're decreasing.
Does that mean for I plus 1, you can then do binary search?
Exactly. That's where we're getting at. Because it's sorted,
Yeah.
I do binary search. All right? So if, let's say it ends up falling in between these two. That's C of I, the cup of length of stall I. What this means is it's now bigger than F3, but F3 is the best, largest cup, that is the largest cup that you can get if you're going to pick 3 cups. So therefore, it's never going to fit in any solution with 3 cups already, which means that that's the one I want to go at. And then, therefore, this is going to give me a cup sequence of length 3. And all I have to do is to figure out whether I want to replace this or not. Well, in fact, I know I will, because we know this is bigger than F3. Right? So now my F3 will become CI, and I can, I know I can do 3 for the ith solution. Does the solution seem to formulate in your head? Yeah? So we could try and do a simple example if you wish. Yeah, that would help. Okay, so let's make up a fictitious example. Let me erase this here, okay? So do you see now that if I can do this more quickly in log n time, I could get n log n, right? So that's where we are going with this, okay? All right, let's try a simple example. You want to give me some numbers? You're not very creative, are you? Are you going to go like this?
No.
How much longer? I don't like this already. Okay, so let's try 7, 1, 9, 6, 5, 2, 3, 4. Am I missing anything? 8. Did I get everything? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay, good. Let's say this is our sequence of cup sizes. So this is C1, this is C2, etc., right? Good. We are going to include a C0. We'll call that 10. That's our infinity, right? And so now we're going to create an array called D, which is our solution for the subproblem that goes from 0 through I, right? And we're going to initialize this to 0. To start with, we're going to initialize this to 1 and see if we can do any better. And obviously, there's nothing here so far, so that's going to be just 1. That means now I have to keep track of F1. Well, let's just put it here. F values are, don't have to move, don't have to move. I'll write it here.
You sure?
Yeah,
Don't mind.
very sure. So let's write down the F values. F values are the best you can do for the last cup in a solution of that size, right? Are you okay with this? Is that confusing or you're okay? Okay, so for this there are no solutions, so I won't have to say anything, right? Actually, sorry, I do have to put in a 10 here because I want all the numbers to be decreasing. Over here, it's going to be 7 because there was only one solution and it's going to be the C1, right? Great. Now, I am going to look at C2, right? Sorry, I'm going to look at I equals 2. And well, I'm going to see where 1 can fit in here. It doesn't fit in anywhere. So therefore, this is just going to be a 1. And I check the solution for 1. and the solution for 1 is 7. It doesn't beat 7, so I don't have to do anything. Is that clear? Okay. Then I go to C3. I look at 9, and 9 comes in between these two. Therefore, 9 is going to give you something of length 1, and it's finally going to improve this to 9, which means there is now a solution of length 1 where the last cup is bigger than before. It's 9. Cool? All right, then we look at 4. 6 is smaller than this. That's great, which means that now I can make this to be 2. Because I can put it in this guy here. And I now get a solution of length 2 where the last cup is of size 6. Until now, I didn't have anything. Yeah?
At C2, why did we get 1? Because 1 is smaller than 7. Where would we have had like a at C2?
Oh, did I screw up? I'm so sorry. Yeah, you're right. What was I thinking? Yeah. So 1 should have been 2. And therefore, this should have been 1. And then when 6 comes in, I throw that out and put 6. Good? Yeah, thank you. All right, then comes 5. And I look through this list, and it can fit in here. So therefore, this becomes 2 plus 1. So that becomes 3. And so now I have a best solution for cups of length of 3 cups. And that's the largest size I can do. Good? Then comes 2, and 2 fits in there, so that can be made 4, and here it's 2. Then comes 7. I look at 3, it fits in right there. So therefore, the best I can do is 3 plus 1, that's 4. But now I can replace this with a 3. Because I have a better solution for 4 cups. Right? Then I have C8, I equals 8. 4 fits in here. And I can replace this with a 4. This is also going to be 4. Then comes 8. 8 fits in there. So therefore, that's going to be 1 plus 1, that's 2. And it's going to replace this with the 8. This is what you end up with. So each time you're doing binary search to figure out where it fits into this array is not of size n. It's only of the size of the largest solution you have. It could be all the way up to n, but in order to do search here, I can use binary search, and it can be faster. So I don't have to try all these guys. I only have to find out where my value fits, and I know exactly what the right solution is going to be. Cool?
Yeah, really cool.
So therefore, with this trick, I can now run this in n log n time. So I am maintaining the highest last cup, or the largest last cup, with k cups for all values of k. So here, this condenses all the solutions I've looked at and tells me where I can fit in. Now, you can create yourself one more problem by saying, find me the set of cups that make up this solution. Should I just leave it as homework?
Yeah. Because we had it, but then we overridden it.
Right.
Mm.
Well, it's something like that. Another simpler way is you have a parallel array called G, where anytime I write something, I also write down its index over there. Okay, so this 9 came from index 3, right? This one came from index 0. This 8 came from index 9. So I'm just keeping track of the index along with the value. 5 came from 5, 4 came from 6. Now, what is the best? Obviously, the best is 4, right? I can take 4 cups. The D can pick up 4 cups. So this tells me what my best solution is. It tells me
4 came from 8 now. So isn't
no, you don't want to work from 8. That's not what you're doing. You always work from the longest solution.
no, but cup 4.
Yeah.
That had
Oh,
4.
I'm sorry, I screwed up. Yeah, I see. Yeah. I was looking at the wrong array. I'm sorry. This should be 8. You're right. Okay. So now, in order to create my solution, what I say is my best solution has length 4, and the last one that the last cup sat in position 8. So that was stall number 8. So this is length, and this is the stall number, or the index, essentially. So this is at 8. Then this should fit in well with the solution of length 3. Solution of length 3 had 5. What did I do? Yeah, it had 5, right? So you would pick up this guy. So length 3, you pick up the guy at position 5, right? Then position 2, you pick up the well, you shouldn't be, yeah, this doesn't quite work because I erased the previous solution and I kind of lost it. So yeah, you're right. So you have to keep track of the parent kind of thing, saying when you did this, which one did you use? But then if you did that, you have to keep track of a lot of stuff. And yeah, so each of these is really a linked list where you only keep track, you're only interested in the last one for the solution. But if you want to retrace and backtrack your actual items, then you may have to figure out where it is that you're going in that list. Yeah. Yeah, it's a little more work than I had thought. So you do have to kind of work your way before. So the previous one is going to be 6, and 6 came from position 4. And then for 1, the best one turns out to be the one from position 3. That's the 9. So you're going to tell D, pick up the cups from positions from stalls 3, 4, 5, and 8. That's the answer. Right? You have to work a little bit harder. I know that what I had there didn't quite work because we overwrote some earlier stuff, but if you keep them in a linked list, you only keep track of the last one, and you can still go back and look at the previous items.
Looking at the previous items, when you come across one that's smaller than what you already have, that's the one.
Correct, exactly.
What
Yeah.
if,
Larger, not smaller.
Oh, no, it's not.
then for G,
Yeah,
we only like update the index?
yeah, that's right.
If it increases B.
If you change F, you also go and change G.
Oh, but what if we don't do that?
These two go together. They're tied at the hip. If you change this, you also change this, because this information is the G information is closely related to the F information.
But shouldn't the G information be the cups?
It's just an index, so it is the cups, sure. This says it's the cup from stall 3, this is from stall 9, etc., etc.
Yeah, so, for example, okay, in G,
Yeah,
the third element, the 9,
yeah,
let's say we didn't overwrite the 6, and the reason we didn't overwrite it is because D didn't get changed, didn't get incremented by 1. If
Yeah.
it actually went down. At that point, would we not have gone in the right order by following
no,
the
so the reason the backtracking didn't work well was because it would have worked if this were longer. Okay, then it's possible that 8 was somehow involved in the answer. It turned out that it wasn't longer, and so this change actually happened after that last change. And that's why the mess happened. Instead of overwriting, if I write it as a linked list, then I always keep track of the previous solutions. And so I just have to work my way backwards from the last guy, that's all. And as he said, you'll look at 8, and you'll see that 8 is bigger than the index you have so far. So you'll go to 6, which is at position 4, and so on. And that's how you work your way backwards. So both this and F and G will be linked list. In fact, you can combine them and make it as a linked list of these records, right? So you would have both values, what the value is and what the index is.
Or you could have just one array being a linked list. And then
Exactly. Yeah. 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 So each item has both the F value and the G value, right? Or as an array, as he said. Yeah.
I have a question. If we're done, there was a question you gave us in our assignment about the MSD problem. I tried solving it yesterday, but I couldn't figure out how to solve that question. Like I know if I were to just minimize.
Did you read the announcement?
Yes.
Clarification.
No,
Okay.
I understand the question. I just
Okay.
don't know
All
how
right.
to solve it.
Okay. So what is your question?
So if I'm given 2 parts, right?
Yeah.
My goal is to minimize the largest edge weight inside of that part. I can simply just find all the parts and choose the one that has the smallest edge weight, right?
Yeah.
Then
Sorry, not the smallest edge weight. It's this. It's the
smallest edge weight.
correct smallest largest edge.
Okay, but the goal is to find like a tree that connects every vertex, right? That has the smallest, largest edge.
No, you're not interested in paths anymore. You're just saying in the whole tree, you want the smallest, largest edge. That's all. It's not when you're connecting things.
Wait, so no, you're not supposed to find the spanning tree with the smallest.
Spanning tree, yes, but not shortest path. So you're mixing those two.
Oh, okay, sorry. So you're supposed to find the spanning tree
Correct.
with
The smallest, largest weight. Weight, yeah.
weight, right?
Yeah.
So how do you go about solving that? Like, I know that the homework was due yesterday, so I thought I'd ask today, but because I couldn't figure it out, like I know how to find that
Yeah.
spanning tree, or if it was just between 2 nodes, right, I could find all the different parts. But since we have to find the spanning tree,
Yeah.
I don't know how to go about solving that question.
Yeah. How can I say something that doesn't really? Well, since everyone is watching this as well, right? So don't keep it on. No, keep it on. So one way, turn the problem around a little bit and say, can you first test whether the smallest, largest edge is W? Can you test this?
Oh, I see. I think there's no one using. Wait, should I say what I think?
Go ahead.
So essentially, you start from the largest edge and check if it is a bridge, right?
Bridge.
Yes, because if it is not a bridge, then it doesn't
Yeah, your ideas are interesting, but that's not quite the right answer. It doesn't have anything to do with bridges.
That's already yesterday, but I couldn't get the solution. I got the other one with the
Yeah.
alteration part.
By the way, this was, you can find this on the internet anywhere. It says that a minimum spanning tree does have the smallest, largest edge. Of all.
All I had to do was just look at and that makes sense because if the minimum spanning tree doesn't contain it's not a minimum spanning tree.
Yeah.
So all I had to do
Now, so there is a problem here. The problem is that minimum spanning trees, the algorithm for finding minimum spanning trees is horrible. Whereas you can find a more efficient algorithm for the problem I asked you. However, a minimum spanning tree is a tree that has the smallest possible largest edge weight. However, a tree that has the smallest possible largest edge weight may not be a minimum spanning tree. You can find other trees that have the same smallest largest edge but are not exactly minimum spanning trees.
that makes sense.
Anyways, these are all things to use. You're free to use these any way you like. But really, if you want to find a more efficient solution, the way you want to start to think about this is, can I test whether the value is 7? Or can I test whether the value is 50? This is the value of the weight of the smallest, largest edge. If the largest edge I need is only 50, what do I have to do to test this? Anyways, go home and think about that.
Yeah, I'll think about that. But the assignment is already, like, the due date has already passed. It was due today.
Yeah, well, you can always turn in that one problem later, right?
Yeah, I will do that. Thank you.
You're welcome. You're not planning to leave these pens here, right?
No. Those are actually from the PPD that were given out.
Yeah? Oh,
Yeah.
very nice, yeah.
Not bad.
They're not bad, yeah. Looks like they may even last longer.
Yeah.
Yeah. These are, you have to keep replacing them.